So we are going to go through these subtopics, determining accelerations of free fall. Okay, so first of all, this experiment is about how we find out the acceleration and the G equal to 9.81, how we find out that value. So to do that, first point, a steel ball is held on an electromagnet. Okay, so electromagnet is attracting the steel ball. Okay, when electromagnet switch off, ball interrupts a beam of light and a timer started. Okay, so there is a, we call it light gate. So the light gate has a beam of light to the sensor. So when the ball block the light, so the sensor detect no light, then the timer start to calculate the time. So that is how it works. As long as the ball block the sensor, then the timer will start the time. As ball falls, it interrupts a second beam of light and timer stop. So the light continue to fall until here, it blocked the light again and the timer stop. So by using this kind of setting, we can calculate the time accurately. Okay, so next one, vertical distance h is plotted against t square. So we are going to plot a graph h against t square. So the graph is going to be like this h against t square. So what kind of graph are we going to get? You look at the equation here, s equal to ut plus half at squared. And we take u equal to 0 because it starts from rest. Okay, from rest, u equal to 0. And then after that, if u equal to 0, the first term disappears. Okay, so that's why it's s equal to half at squared. And then after that, the s replaced by the h here. So you get h equal to half at squared. And from here, we know that this is the y-axis, this is the gradient, and this is the x-axis. So we get the equation y equal to mx. So we need to know that y equal to mx is a straight line from origin. So you should expect your graph to be a straight line from origin. And if you go and count the gradient is equal to 1 over 2a. Okay, you count the gradient of the graph, then you let it equal to 1 over 2a, then you can count a. So basically a is 2 multiplied with the gradient. So that's why it's written here. Accelerations is equal to the 2 multiplied with the gradient. So you will get that. So that is the whole experiment. So we have done this part, the experiment which talk about how we find out the G. Okay, so acceleration due to gravity. We discussed through some questions first on this experiment. So there is some question on this. So let's go through. Of course, for the question we discussed right away. So let's get question 9. Two markers M1 and M2 are set up a vertical distance h apart. So you can see M1 is here, M2 is here. But the thing is, M1 is not the starting point. It's somewhere after a distance of x. Okay, so when a steel ball is released from rest, so it's here, u equal to 0. From a point distance x above M1, it is found that the ball takes time t1 to reach M1. So take this amount of time to reach M1, and time t2 to reach M2. Which expression gives the acceleration of the ball? Okay, so let us go through this. So we use S equal to UT plus half AT squared. So we know that U equal to 0. Let's take the displacement at this part. X. The displacement is X. The time is T1. It's T1. Okay, so we substitute the displacement with X. Substitute the UT, the U with 0, and the whole term disappear. Half A. The A will be G, of course, it's G. Okay, so we let the A equal to G. Okay, G. And then followed by T1 square. Okay, so we get this. And let's say I just call it equation 1. Okay, now I'm going to set up another equation. So I use U equal to 0. Now my displacement, I let it be X plus H all the way from the starting until here. So X plus H. So in that case, the time is going to be T2. The acceleration is still G. Okay, now we substitute X plus H equal to, again, the UT disappear because U is 0, half G T2 square. So we get something like this, and I call it equation 2. Okay. So basically, what we need to find is the G. We want to find the G, and if you look at the A, B, C, D here, there is no X. So we are going to eliminate the X by using simultaneous equation. So we substitute 1 into 2 so that this one can replace the X there. So we get half GT1 square plus H equal to half GT2 square. So we get this. And after that, let's say I multiply with 2. I multiply with 2 to get rid of the half. GT1 square plus 2H GT2 square. So I want to get G in terms of others. So I gather out the G. I put the G on, let's say I put the G on the right. So 2H equal to GT2 square minus GT1 square. Factorize the G. T2 square minus T1 square. And after that, divide 2H divided by T2 square minus T1 square. And then you get G. So we look at the answers here, the choices. So you will realize that it is D. Now, let's go through this. Okay, so this table is about the free fall again. Okay, the free fall. So when you release, imagine when you release an object and let it fall freely under the gravitational accelerations. Okay, so we want to see it in terms of displacement, velocity, and acceleration with two situations. The first situation is without air resistance, and the second situation is with air resistance. Okay, so you see the difference is like this. When there is no air resistance, so the force that pull it down is basically the weight. The weight. Okay, so if there is air resistance, the object has weight that acts downwards, but the air resistance, which is also a force in the opposite direction, the air resistance act upward. So the difference is the net force is just equal to W, but for this, the net force is equal to W minus A resistance. Okay, so there's a small difference because of this. So you should expect this to be smaller, because there is an A resistance there. This is bigger than this one. Okay, now let's see the information here. Displacement, the rate, the sentence in rate is without A resistance. Okay, so without A resistance, what happened? Continue to curve as it accelerates. Okay, so of course it accelerates because uh, we have weight that act downward. Then W equal to ma. So this is a fixed value. W is a fixed value. So hence acceleration is also the fixed value. So it's a constant for both. Okay, so there is an acceleration. So if you still remember, if acceleration is happening, the graph of s versus t is a curve. So if there is an air resistance that acts on the object, we look at the blue sentence here. Graph levels off. Levels off, that means become straight line. As it reaches terminal velocity. So that means the graph is a curve at the beginning and then it becomes straight line afterwards. Of course, what happened here is we need to know that the air resistance is affected by velocity. Okay? Affected by velocity. So as the object falls down, it is getting faster and faster. So the velocity is getting greater and greater, and the air resistance is also getting greater and greater. So at one point, the air resistance is same value with the weight. In that case, I write it down first. So velocity increase, air resistance increase, then air resistance equal to the weight. So when this happens, the net force is equal to 0. So when net force equal to 0, net force is equal to ma based on Newton's second law. Then the A is also equal to 0. So when A equal to 0, that means there is no acceleration. And in that situation, we call it, no acceleration means constant velocity. So the constant velocity over here is equal to terminal velocity. We call it terminal velocity. Terminal velocity. So terminal velocity is constant velocity. So we know that when there is no acceleration, constant velocity, the graph is straight line. So that's why it becomes straight line. It is curved at the beginning because it still accelerates. After that, it becomes a straight line. That means no acceleration. Okay, so we continue. Velocity versus time graph. Without air resistance, it's a straight line. So if you still remember, if your VT graph is a straight line, that means there is acceleration, constant acceleration, continues to accelerate constantly. But with air resistance, the object will reach terminal velocity. So that's why it accelerates. After that, it flattens, become horizontal. Horizontal means constant velocity, which is terminal velocity. Graph curves as it decelerates and doesn't decelerate actually. Decelerate is wrong wording here. Okay, it's a wrong wording. It's not decelerate. It is moving faster and faster until a particular speed. Then it never increase in speed anymore. Okay, so we should do correction on this. It is not a deceleration. It is where acceleration acceleration decreases to 0. Acceleration decreases to 0, then in that case, it reaches terminal velocity. Okay, so it's not decelerate, it's decreasing in the acceleration. Okay, and then to 0, then we reach a speed which is terminal velocity, and level off to terminal velocity. So that's how it become horizontal after that. Okay, now we look at the third graph, acceleration versus time. So for the red one, without air resistance, it is a straight line, showing that it has a constant acceleration of value 9.81. So for the blue one with air resistance, the acceleration decreases. So that's how you can see the acceleration keep decreases. From 9.81, it decreases until 0. Until 0. Until 0, when it is 0, terminal velocity achieved. When a equal to 0, we call that terminal velocity. Okay, so we have 3 situations. You learned the graph already. Now you applied it in this situation and it should be easier to take it. Okay, so we finished this part already. Let's move on. Okay, the next part, projectile motion. Projectile motions is where we throw a ball in horizontal, but because of the gravity, the ball will not remain in horizontal all the time. The ball will move in this particular curve. Because of gravity, it falls in this way. So we call this projectile motion. So you see here, uniform velocity in one direction. In what direction? In the horizontal direction. In the horizontal. Horizontal. The horizontal component is uniform velocity, is experiencing uniform velocity. So you see it in this way. The actual motion is the red one. Okay, but the thing is, we bring it down to the green one to see what happened. Okay, we bring it up, 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 and up. Then you will see they are having same distance from each other, meaning that it has a uniform velocity. And constant acceleration in the perpendicular direction, that is the vertical. For the vertical component, it is having the gravity, the gravitational force to act on the objects. And because of that, it accelerates. So that's why if you see this, this is the actual motion. Then you bring it to the side. For analysis purpose, we bring it to the side, to the blue balls there. Okay, then we will realize the ball is getting further and further apart, showing that it is getting faster and faster. Okay, vertically it is getting faster and faster. So from here we know 2 situations. Okay, so I put it in a table. For the horizontal component, I use H. H to represent horizontal. The horizontal acceleration is 0. But for the vertical I use V. The vertical acceleration is equal to G. So it's equal to G. So which is 9.81. Okay, so what else we know? So we also know that the horizontal initial speed is, you throw your ball in horizontal. So you throw your ball in horizontal. So let's say the speed is u. So the horizontal velocity is initial velocity u also. But vertically, it doesn't fall down initially. Initially it's moving in horizontal, so it doesn't move down. It moves down after a while, because of the gravity. So initially, the vertical initial velocity is 0. So you try to compare, it's 0. This one is u. The final horizontal velocity is also u. It's also u because it's having uniform velocity. So the velocity is u all the time. Okay? U all the time. We assume there is no air resistance. So that's why it's u all the time. Okay? But for the vertical final velocity, so we need to count it. We need to count. So how we count? We use formula, the Subat formula to count. We need to count. Okay. So for example, you can use V equal to U plus AT to count. You can use V equal to U plus AT. Substitute the vertical component for your U, for your A, then you can count it. So you try to imagine your vertical initial velocity is 0. So you get G multiplied with T. Then you can count. Substitute 9.81, substitute the corresponding time, then you just find out the final vertical velocity. So you can just count it that way. So that's how we count it. Okay, now let's continue. The displacement, the horizontal displacement is equal to ut. You try to imagine s equal to ut plus half at squared, the formula. The a is 0. Acceleration, horizontal acceleration is 0. So that's why these second terms disappear. Only ut that remains. So horizontal displacement equal to u times t. U times t. Okay. So of course the other way to take this is you just use speed equal to distance over time. But be careful, this formula is true when there is no acceleration. So speed equal to distance over time is true when there is no acceleration. So it's suitable to be used for horizontal component. So speed multiplied with time, you get the distance. So that's how you see here, speed multiplied with time. Then you get the distance. Okay. Now for the vertical displacement, we need to count it in this way. We use this formula. Okay, but the u is 0. The u is 0. The vertical initial velocity is 0. So then we have half g t squared. Then we get this. Okay, so since I have Vv equal to gt, okay, I put it inside also. And then you can get every information in a complete way. Okay, so this one is gt. So okay, so we have done this part. Okay, now let's continue with this point here. Horizontal motion, constant velocity. Constant velocity is the same. The velocity is the same. Speed at which projectile is thrown. Okay, so the speed where you throw the ball, that speed will remain until the end in horizontal. Vertical motion, constant acceleration, which is 9.81. Caused by weight of object, constant free fall acceleration. Okay, so which is 9.81. Okay, now we have the second type of projectile motion, so which is this way. You don't throw your ball horizontally, but you throw your ball in a particular angle, pointing upwards. And then it will just move as a curve and come down. Okay, so this is parabolic shapes. and it follows a quadratic y proportional to x squared. Okay, so let's discuss this part. Let's say you throw the ball in this direction. In this direction, u, and here theta. U and theta. Okay, now we have to take it in this way. Okay, I draw a table also, with two parts, horizontal and vertical. Okay, so I do the horizontal and vertical in this way. We do resolution. This is the U. Then we have a right angle triangle. The horizontal is this one. The vertical is this one. Okay, so the theta is here. So we know this is the adjacent thing of cos. Adjacent over hypotenuse is cos theta. So we rearrange it. So this is u cos theta. And this is opposite. Opposite over hypotenuse is sine. So you think of, you rearrange sine theta equal to opposite over hypotenuse, then you will get the opposite as u sine theta. So we get the horizontal and the vertical initial velocity. Okay, so we write it down first. For this kind of projectile motion, so the horizontal initial speed is u cos theta. U cos theta, which is this one, as you can see here. The vertical initial velocity is u sine theta. U sine theta. Okay. This one is pointing upwards. It's pointing upwards. So if you still remember our discussion previously, where I mentioned if the motion involve up and down, so up is normally taken to be positive, down is negative. Up is positive, down is negative. So we need to apply it for this situation. Just now for this, we don't apply up to be positive, down to be negative, because it is no upward motion. It is just down all the time. We assume down to be positive. So that's why our G can take 9.81, because we assume down to be positive, as there is no upwards motion. So to make ourselves more convenient, we assume down to be positive. Okay, but now we have up and down, we have to assume up to be positive, down to be negative. Then the acceleration due to gravity is hence negative 9.81. Because this is positive, right? So this has to be negative as it's downwards. But horizontal acceleration, no value. Okay, if you want to find out the final horizontal velocity, it's the same value. Same value because no acceleration. It's a constant velocity. But for the vertical final velocity, so you have to use this formula. Imagine ut, okay, v equal to ut u plus at, so the u is u sine theta, the a is this one, negative 9.81 t. So we can do it like that. Okay, so based on this formula, u sine theta is the u, then minus 9.81 is the a, then followed by the time. Okay, so after that, if I want to find the horizontal displacement, you know there is no acceleration, and I can use this formula, distance equal to speed times time. Or you can use this and assume a equal to 0 and end up with ut. So the u is u cos theta. multiply with time. Okay. For the vertical, so what we have is we use this formula again, ut plus half at squared. So the u is u sine theta, ut multiply with the t plus half. The a is negative 9.81 multiply with t squared. So we get this formula. So altogether, we have two sets of formula. So the first one is for this kind of projectile motion. The second set here is for this kind of projectile motion. Okay, so let's finish up the information first. When we go through the two sets of formula here, we assume that there is no air resistance. No air resistance. But if there is air resistance, so how is it? Let's see. Component of velocity without air resistance, horizontal is constant. Constant. That means constant velocity. You see, the velocity is the same before and after. This one also same. Initial and final same. Constant. Vertical component increases at a constant rate. Increases at a constant rate. Without air resistance, there is a constant acceleration of 9.81. Constant acceleration. So that's why the velocity increases at a constant rate. With air resistance, the air resistance basically will be the force that acts opposing the motion. So it will slow down the object. Okay? The horizontal velocity decreases to zero because of the air resistance. So it makes it slow down to zero. Okay, decreases to zero. Okay, so that means initially is u. At the end, it will keep moving slower and slower to zero. Increases to a constant value. This constant value is the terminal velocity. Terminal velocity increases to a terminal velocity. Terminal velocity. Okay, so these are all about projectile motions. So to practice this, let's take a look on the questions. Okay, so let's see this. We discussed this straight away. A golf ball is hit so that it leaves the club face at a velocity of 45 meters per second at an angle of 40 degrees to the horizontal. Okay, so that means it is going to be this kind of projectile motion. And initially, imagine I'm drawing a tangent to the curve. So it's 40 degrees from the horizontal. And then the U is 45. Okay, 45. So now I'm going to do resolutions of the velocity to find out the horizontal and the vertical component. Okay, so let's see what they ask first. Calculate the horizontal component of the velocity. Horizontal is the adjacent. Adjacent is involving cos. So it's 45 cos theta. So which is 45 cos 40 degree. Then you press calculator, you get 34.5 meter per second. Okay, now we look at B. The vertical component of the velocity. Vertical component, remember this is opposite of the angle involving sine. So 45 sine theta, which is 45 sine 40 degree. Press calculator to get 28.9 meter per second. Now C, the time taken for the ball to reach its maximum height. Its maximum height, which is here. Okay. So what time does it take to reach here? Okay. So to determine this, we need to understand one important concept. For maximum height, the vertical final velocity is 0. Vertical, I write h, that should be v. Vertical is v. The vertical final velocity is 0. So we consider the vertical component. The vertical component. So what we can use is we want to find the t, right? So we have, for the vertical component, we have u equal to 28.9 from part B. We have a equal to negative 9.81. We have v equal to 0. So we are looking for t. So we use v equal to u plus at for the vertical component only. So we substitute 0, 28.9, negative 9.81 t. And then we just calculate, find t. Is over that after rearrange. So we get 2.95 seconds. So that is part C. Now part D, the horizontal distance traveled when the ball is at its maximum height. Horizontal distance, that means here to here. Horizontal distance. So we have to look at the horizontal information that we have. Horizontal means there is no acceleration. Then the time is this time also. The moment when the ball reached the maximum height is the moment where it reached this point horizontally. Okay, so 2.95. So we are looking for the S. We have the U. The U is 34.5 for the horizontal component. So we use S equal to UT. The half AT square is gone because of the acceleration is 0. Okay, so S equal to 34.5 times 2.95. Then you will get 101.8 meter. So like that. Okay. Okay. So this is projectile motion in this particular way. Okay. Now a stone of mass 56 grams is thrown horizontally from the top of a cliff with a speed of 18 meters per second, as illustrated in figure 4.1. 18. Okay, so for practice purpose, I do like this. Later when you go for exam, no need to put so much of details. So vertical and horizontal, I separate first. The horizontal is 18. The vertical initial speed is actually 0. Compare 18 and 0 because initially it's not going down yet. It's still in horizontal. So acceleration is 0. But this one, acceleration, you can take 9.81 because we can assume down to be positive. As the thing is just going down all the time. So assume down to be positive, hence 9.81. And then final velocity, don't know yet. We need to count. Okay, final velocity for this is 18. But final velocity for this you have to count by using v equal to u plus at. U is 0. U is 0. A T. Displacement, just take ut for this case, 18t. For this, u is 0, right? Disappear. Half a t squared. So I put every information here. Okay, now let's see. The initial height of the stone above the level of the sea is 18 meter. So this seems like it is the vertical displacement. A resistance may be neglected. State the horizontal velocity. Horizontal velocity 18. So 18 as it hits the water. So no matter initial or final is just 18 only. Final is where it just before it hits the water. It's also 18. So on the grid of figure 4.2, draw a vector diagram to represent the horizontal velocity and the resultant velocity of the stone as it hits the water. Okay, so that means we are going to draw in the graph. Okay, we are going to draw in the graph. What should we draw? We have to draw. You see the question again. In that graph, we have to draw a vector diagram to represent the horizontal velocity. This is VH. It's final velocity because it's just before it hits the water. And the resultant velocity. How to draw resultant? Resultant velocity is actually the horizontal plus the vertical final velocity equal to the resultant velocity. Okay, so horizontal, no problem lah. Horizontal we know already. Horizontal final velocity is 18. So VH is 18. How about VV? VV we have to count. VV, we have 9.81 times t. But the thing is we don't know t. We can't use this now. We don't know t. So we use another formula. If you don't know t, v square equal to u square plus 2a s vertical component. Okay, everything in vertical component. Okay, so we use this formula to find the v. Okay, so we substitute. Vertical initial speed 0. 2. Acceleration 9.81. Displacement 16. Okay, then we just use calculator, count these three values and square root. So at the end, we get 17.7 meter per second. Okay. So with 18 and 17.7, now we can go straight to the graph and draw it out. Okay. So when we draw this, so of course, you need to know here to here is basically 1 cm. Here to here is 1 cm. So we just set our scale in this way. Let's say 1 cm represent 2 meter per second. So our horizontal is 18. So we should do 9 cm. 9 cm. So we draw a horizontal velocity 9 cm. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 cm to reach here. And then vertical is 17.7. 17.7 divided by 2. 17.7 divided by 2, we get 8.85 cm. So 8.85. 1, 2, 3, 4, 5, 6, 7, 8, 8.85. Okay, so then we draw our resultant velocity from the starting point to the end point. Okay, so this is the horizontal. VH 18 meter per second. This is the vertical VV 17.7 meter per second. This is the resultant VR. Okay, so use your vector diagram to determine the angle, with the horizontal at which the stone hits the water. So this angle with horizontal. So we want to find that. Okay. So they say use your vector diagram to determine. So that means you have to use protractor to measure. So of course, if you are not using protractor to measure, you can just easily use tangent theta to count. Tangent theta equal to opposite over adjacent. Then you can get a theta, inverse tangent, and take this value. Then you will get 44.5 degree. Then we fill up here, 44.5. So that is how we handle the projectile motion. Okay, so we settled this already. Okay, so we go through this now. Motion of a skydiver. What we need to know is skydiver is the person who jumped down from the aeroplane. So of course he is not going to jump down and like that only. So after a while he had to open up his parachute so that he can fall down at a slower speed and safe. Okay, can land safely. Okay, so let's see the graph and understand terminal velocity and the force. Okay, so first, when the person jumped down from the aeroplane, he accelerates. So that's why the graph is like that. But the thing is, that person experiences air resistance. Air resistance. As what we discussed before, air resistance is affected by velocity. So when it accelerates, it's getting faster and faster. When it is faster and faster, the air resistance is getting greater and greater also. So that is what we need to know. So because of that, the weight which act downward minus with the air resistance which is getting greater and greater. So you should expect the net force, which is W minus air resistance. This is getting greater and greater. And because of that, this net force is getting smaller and smaller. Okay? And you know, net force is equal to MA. So if this is getting smaller and smaller, the acceleration is decreasing. Acceleration is decreasing. And you need to know that this is velocity versus time graph. So if the acceleration decreases, the gradient which represent acceleration in velocity time graph. So acceleration decreases, the gradient of VT graph decreases. So that's why you can see the gradient keep decreasing. The gradient is basically the gradient of the tangent as it is decreasing. Decrease until it is zero gradient. Zero gradient. So this is a steady speed. So you can call this terminal velocity for temporarily. Terminal velocity. So after a while, now this is the point where the parachute is open. The parachute is open. At that point, You know, parachute has a large surface area, so which increase the air resistance. Okay, so because of that, it slow down, decelerate, slow down. Okay, decelerate, and the air resistance and the weight again balance off at one point, so it achieves steady speed again. Okay, steady speed. Now it falls down at steady speed with smaller value compared to just now without parachute. With parachute, it's fall down slower, and this is the steady speed of the terminal velocity again. So after that, in a sudden, it stops. It stopped in a sudden because this is where landing happened. So it stops in a sudden. Okay, so this is the whole graph, which involves skydiver. So we have done the theory part. Okay, so now we discuss through a few questions in these chapters. So let's look at this. Question 6. In still air, a bird can fly at a speed of 10 meters per second. The wind is blowing from the east at 8.0 meters per second. In which direction must the bird fly in order to travel to a destination that is due north of the bird's current location? Okay, so let's see. The bird is trying to go to the north. That is what we call the resultant. The resultant is to the north. Okay. Now the wind is blowing from the east. You know, from the east means from the east to the west. So that means it's like this. Okay. So this is east to the west. From the east to the west. So this is the wind. The wind is blowing this way. The resultant is this one. This is one of the component. Okay. So because of that, the bird have to fly in a particular direction, which is going to be like this. The bird fly this way, and then the wind blow it to this way. So we are using vector, and this is about vector. Okay. The bird fly this way, the wind blow this way. The resultant is move straight. So that is the resultant. So this is 8.0. This is the speeds of the bird, 10 meters per second. Okay. Now they are looking for the direction. So the directions, okay, theta that means the directions the bird fly. That means this one. So we are looking for theta. So we use tangent. Sorry, we use sine. Yeah, opposite over hypotenuse. 8/10. So we count theta, inverse sine 8/10, you get 53 degree. 53 degree, two options. East of north, west of north. So this side is east. East of north. So this one, C. Okay, now let us discuss another question here. An archer shoots an arrow at a target. So projectile motion. Okay, so the diagram shows the path of the arrow. Air resistance is assumed to be negligible. The graph shows how three different quantities, P, Q, and R, relating to the motion of the arrow, vary with time. Okay, so you can see this one, horizontal. Horizontal. So what is constant? We need to figure out. Okay, so based on the the choices. Based on the choices, you see the choices at the same time. Horizontal component of displacement, vertical component of displacement. So these are the two choices given. So we determine from the choices which will make our life easier. Okay, horizontal displacement and vertical displacement. Okay. So can it be constant? Of course, no, because horizontally it is going forward. The displacement is getting greater and greater. Vertically it is going up and then going down. So cannot be constant. The constant here is actually the velocity, horizontal velocity. Horizontal velocity is constant. So this one is out. Okay. Q increasing should be horizontal displacement as they go forward only. So this is horizontal displacement. This one going up and down. That is the vertical displacement. Vertically, it goes up to the maximum height, then it come back down to the horizontal. So go up and down. So this is the vertical displacement. So from here, we can determine Q as the horizontal, R is the vertical. So the answer should be B. Should be B. Okay, so let's see another questions. So again, we discussed through this also. A stone is released from rest and falls a long distance in air. So when they say a long distance in air, they are trying to expect you to know that it reaches terminal velocity. Terminal velocity, terminal velocity happens after a while. Which graph could show the variations with time t of the accelerations a of the stone? Acceleration. Okay. So if you still remember the theory, there are weight acting downwards, there are a resistance acting upwards. So the net force equal to weight minus a resistance. So this is getting larger and larger as the object is faster and faster. Then this is getting smaller and smaller. Then F net equal to MA. If this is smaller, this is smaller also. So you should expect the acceleration to decrease. Okay. So acceleration to decrease. This or this, B or D, B or D. So these two out, cannot be, either B or D. Decrease in which way? So if you still remember the note, if you still remember that, in the notes we have the discussion of this on page 2. On page 2, so it should be D. You can see the note. It's D. Okay. Now let's see one more. A football falls from the top of the tall building. Which graph best represents the way in which the distance x fallen varies with time t? Okay, so free fall. Free fall. Let's see. So we have distance x with time t. Distance x with time t. Okay, so acceleration happenings. Acceleration happening. So we should expect curve. This curve or this curve. So this curve, then here become vertical. Cannot be. Should be this. This curve. Here is curve. Here is accelerate. Then here straight line. Straight line means terminal velocity. So it should be D. Accelerate but the acceleration decreases, then the gradient is getting smaller and smaller, and then no, not gradient, okay? So it's a curve followed by straight line. Okay, it's not gradient. Gradient is for velocity time graph. Okay, so we settle already. Okay, now let's see this also. Two identical cars P and Q are traveling along a straight line, a straight road. Car Q is traveling at twice the speeds of car P. Twice. The brake are applied to both cars, providing the same constant deceleration. Constant deceleration. This constant deceleration is important. Which graph shows how the velocity v of each car varies with time t? Okay, so we have two information. Twice the speed of car q. So initially this must be twice. So it seems like okay for all of them. Then this twice is not an issue really because the graph shows twice for all the graph here. Constant deceleration is the main consideration which determine the answer. You know, when the graph is velocity time, gradient is the acceleration. So we should expect negative gradient because deceleration, constant deceleration must be a straight line. Constant deceleration is a straight line. So negative gradient and straight line. So it should be C. So like that. Take vertical upward as positive. Vertical upward as positive. That means down is negative. Okay, so acceleration of the ball at various stage in its motion. You throw the ball vertically upwards and then it fall down. Something like this. So no matter which point, at this point, or this point, the A is negative 9.81. Even here, negative 9.81 at this point. Okay, maybe you feel like, it's not moving. Yeah, it's true, it's not moving. But when it's not moving, is V equal to 0, not A equal to 0. A is still negative 9.81. Okay, so we need to know that because what acting on the ball is the weight. So there is no air resistance. No air resistance. Ignore air resistance. So the net force is equal to MA. So the net force is W. W is the net force. So because of that, mg, right, equal to ma. So then you cut. So the A is always equal to G. So because of that, it is B. Always negative 9.81.
Oh.
Yeah, always negative 9.81. Compared to just now, number 7, there's a quick discussion. Number 7, right? Air resistance is there. If air resistance is there, F net equal to W minus air resistance. Then net force is MA, W minus air resistance. So this decrease, then this one will. So I mean air resistance increase as it's getting faster and faster. So acceleration will decrease. Acceleration will decrease to 0. Will decrease to 0 at terminal velocity. So this one will decrease. That one constant because no air resistance. No air resistance, this is constant. With air resistance, this one will decrease. So remember that. So that's why this one will decrease to 0. But that one will not decrease to 0. Will just remain the same because it's just weight which affect the acceleration.